So welcome back. I forgot to tell you that it's a tradition in China that after the introduction of the speaker, we applaud the speaker. We don't have this tradition in Brazil, but we can adopt it for this week.
Oh, no, don't have to. I mean.
So it's my pleasure to introduce YuanYuan Chu from the University of the Academy of Science in Beijing, and she will give a course on random matrices. So let's welcome YuanYuan.
Hey, thank Claudio very much for this kind introduction, and it's really my honor to be here and to deliver lectures on random matrix theory. So I would like to apologize because this lecture is designed for non-expert in random matrix theory. So if you happen to be the expert in random matrix theory, I apologize. You may find the content a bit disappointed. So I hope that I will present some clean result in random matrix theory with elegant proof. Elegant proof means that we can complete the proof in a short time. And I hope you will find random matrix theory interesting and wish to explore more after these lectures. Okay, so from the name, you can tell that random matrix theory is simply to study matrices that are randomly chosen. So the very first question is how to construct a random matrix, right? There are quite many ways to construct a random matrix, and maybe the most direct way construct a random matrix. The most direct way is to know the joint distribution of the matrix entries, right? Of the matrix entries. And usually we will often assume that the entries are independent from each other. Do I have another color? Okay. So the most famous model is called Wigner matrix. Maybe someone in the audience has already heard this name before. So it goes back to a physicist, Eugene Wigner, in 1950s. He introduced such a model as a toy model because he observed that actually the eigenvalues of the Wigner matrix, eigenvalue of the random matrix, behave similarly like the energy levels of the atomic nuclei. So it's the energy level of atomic nuclei. So it behaves similarly in the sense that we know that the energy levels are usually repelling each other, right? And the eigenvalues of the random matrices also have this property. They are repelling each other. You will see it later. Okay? So it's like the eigenvalues, they are repelling each other. Okay? This is very important. And so besides this motivation of studying the energy levels, actually the random it turns out that the Wigner matrix it is very rich itself in the sense that it shows it has universality. So the eigenvalue behavior of the Wigner matrix, usually you will observe some universal behavior. I say universal means that the property, so the distribution of the eigenvalues does not depend on the distribution of the matrix entries you put here. You just assume they are independent, but you didn't assume that the matrix entries satisfy a certain distribution. You can choose any distribution, you will always end up with a similar phenomenon. So this is called the universality. Actually, this universality is, exists beyond random matrix model. What does this mean? So the behavior of the random matrix, the eigenvalues of the random matrices, somehow they have some similarities, share some similarity with other models in the related fields. For example, in a number theory, we all know the very famous Riemann zeta function, right? And the zeros is conjectured to, the non-trivial zero is conjectured to lie on this line, right? It's conjectured to be non-trivial zeros, conjectured to be shows up on this vertical line. And it was observed by Montgomery and Dyson in 1970s, I think. They found that actually the distribution of the non-trivial zeros on this line behaves quite similar to the distribution of the eigenvalues of the random matrices. So this is quite mysterious, right? Because the random matrix model is quite far away from number theory, from the Riemann zeta function, right? And this relation remains mysterious till now. We have no good reason why it is correct. Maybe the most naive explanation is that because eigenvalues are repelling each other in a fancy way, and it looks similar to, actually later you will see that actually the eigenvalues, they have the log interaction between them. Maybe that's the reason why maybe the zeros of the Riemann zeta function, they also have this log interaction. It could be the reason. And so in addition to number theory, so the random matrix theory also has connection with the random geometry. I would say, for example, if you have some random growth model, you look at the height function, right? And you want to see how the height function fluctuates. It also related to random matrix theory. So I see, for example, it's like the KPZ universality. If some of you have already known that before, okay. And blah blah blah. So actually, the random matrix theory has a lot of connections with many related areas. Okay, so I hope this short explanation will convince you that the random matrix theory is really important, and it's also very simple because the construction and the independence assumption. So we should really know how to study random matrices. It's a very natural question, I hope. Okay, so now let me first give the definition of Wigner matrix. Model. So first, it's a Hermitian model. So we assume that this Hn is a n-by matrix. And we always assume that Hn is symmetric, Hermitian. So this means that only the diagonal terms and the off-diagonal terms, they are random variables, and this part is determined by this part automatically. Okay, so you only have n times n plus 1 divided by 2 minus 1 random variables. You can also remove this assumption. You just assume that all the matrix entries are ID random variables without this symmetry constraint. There's also a famous matrix model according to that. But then in that case, the model is in general is not Hermitian, so that eigenvalues are complex valued. Okay, so in today's talk, we will only focus on the Hermitian model. We always assume that's a Hermitian, so that eigenvalues are real valued on the real line. Okay. And for simplicity, we just assume that the matrix entries, they are ID copies of the same distribution. I say chi. Okay. Just assume they're ID copies. Okay. Oh, sorry. Here I should say is just the diagonal terms and off-diagonal terms. Okay. And then I need to put some assumptions on the distribution. So the first assumption is quite natural. We just assume that the distribution is centered. Expectation is 0. And then I assume that the variance is always normalized to 1. If it's not 1, you just divide by some constant to make it to be 1. It's enough. And the third condition is more a technical condition. Usually it's not needed. We just assume that the distribution of chi is the chi is a sub-Gaussian distribution. Sub-Gaussian means that it means that there exists some constant c such that the probability that the chi is bigger than some constant t is bounded by c to the c t squared. That's the definition of sub-Gaussian. So usually this condition is not necessary, but we assume it for simplicity. Okay, it will make the proof and arguments shorter and cleaner. Okay, and then I will say the real Wegener ensemble means that all the matrix entries are IID copies of x, of chi, sorry. Here I forgot to mention that this is a real valued random variable, okay? So if it's real valued random variable, then you define the real Wegener matrix. And you can also define a complex Wegener matrix. You just assume that's the real part of the entries and the imaginary part of the entries. Sorry. IID copies of x chi divided by square root of 2. Here I divide by square root of 2 because I want to make sure that the variance is always 1. Okay, so first I fix my distribution. Okay, and I choose independently from this distribution to construct the real Wegener matrix and the complex Wegener matrix. Okay, and the goal is to study the behavior, the eigenvalue behavior of the Wegener matrix as the dimension goes to infinity. Okay. Yes? That's true. Here, so for the complex case, these are complex valued, but on the diagonal one, they are just the real valued random variables. So maybe I should, no, this one. Yeah, I should be careful. So this is less than I and the HII. Yeah, maybe that's better. So the diagonal, they are real, and off diagonal, you have the real part and imaginary part. Thank you. Okay. And the goal is to study the eigenvalue behavior as the dimension goes to infinity. Then the first question is, what is the correct normalization of Hn? Because you let n goes to infinity, right? You have n square random variables. So the spectrum will blow up as n goes to infinity, right? If you do not do any normalization, then you cannot do any study, right? So any guess for the correct normalization? Just an easy guess. How should we normalize it to keep the spectrum of constant order as n goes to infinity? Is there any brief guess? Okay. I will just tell you an answer. The answer is that we should normalize. We should try Hn divided by square of n. N is the dimension of the matrix. So why this is correct, actually there is a very short explanation. So we simply look at, okay, so we just denote the eigenvalues here by lambda 1 to lambda n, because they are all real values, so I can order it, right? I can order it in an increasing order, okay? And then we can try to compute the average of the square norm of the eigenvalues. I can try to compute that one, right? This is always positive. I take the average. So this should give me the size of the spectrum. I want to keep this one as of order 1 is equals to infinity, right? And what's that? This is simply the 1 over n times the trace of h squared, right? hn divided by square root of n squared, right? And we know that this one is Hermitian, right? So they become 1 over n squared trace h times h star, right? And we can write it out as matrix entries, right? So it's the hij absolute value squared. Then you have the law of large numbers, right? Because they are all independent. So by law of large numbers, it will converge to the expectation. So what is the expectation? It's exactly 1 of constant order. You see? So this means that this should give us the correct size. It should give us the correct normalization for random matrices. And the first effect, there's a very nice result, says that there exists some constant C such that the largest eigenvalue of the matrix, if you normalize in that way, the largest eigenvalue of this matrix is always bounded by this constant, almost surely. It's the first fact. And I will show you how to do that. It's quite simple, actually. So let's just recall the definition of the largest eigenvalue. This is simply the operator norm of this matrix, right? Largest, because Hermitian. Okay? And this is simply the maximum among all the unit vectors which is the y is a vector, the y star hn divided by square root of n, and the y. Right. It's the definition of operator norm. Because it's Hermitian, sorry. And we can write it out. Actually, it's 1 over square root of n maximum among all these vectors. I just simply write it like that. Among all the unit vectors. And this guy will become summing over I and j and a yi times yj. Yi means the ith entry of the vector y times the hij. Right. I just write it out. Okay. So if I first ignore this maximum, I just pick one vector, unit vector. And you assume that hij, they are independent and they are sub-Gaussian. So there are some concentration inequality for this sum, right? Okay, and we use the concentration inequality. So I just fix one vector, unit vector. Okay. Then we know that the probability is such that this guy summing over ij, yj, okay, hij, and here I divided by square root of n, so it's bigger than square root of n times t, right? Or maybe yeah. So this is a probability such that the normalized sum is bigger than t, right? Okay? And they are independent, and you have sub-Gaussian. So you immediately get that there exists some c and c such that c is bounded by c e to the some small c and t square. Sorry, this is square root of nt. square of n t square divided by the sum, the L2 norm of this guy. So the ij yi yj square. This is a concentration inequality, right? And we know that the y is a unit vector. So this guy is simply 1, right? So you will get c times e to the c, small c, times n t squared. Okay, so here you can see that if t is bigger than some constant, then it is exponential small, right? Okay, but here be careful because we only pick one fixed vector, right? This is not enough because here we have to, in order to get the operator norm, we have to take the maximum. Then we just use some standard epsilon net argument, right? So the epsilon net argument. So I just choose I just pick or choose an epsilon net on the sphere. So simply all the unit vectors. I just choose an epsilon net on this sphere. Here I denoted by maybe the pi epsilon. Okay. Epsilon net means that for any element on this sphere, I can always find a net point belong to that, say P belong to this one, such that the distance between this point and this point is bounded by epsilon. Okay, distance is bounded by epsilon. Definition of epsilon net, okay? And by some easy computation, you can also show that the number of the lattice of the net point. So the size of the net point is bounded by some constant c, 3 divided by epsilon to the power of n. N is a dimension. Okay. Then we just want to, because here we already know that for each lattice point, for each net point, we can have a very good control on the tails, right? And now we pick any vector on the sphere, and we want to use this net point to approximate this one. So how do we do that? We just look at the y star hn divided by square of n y, right? And we just write this as p plus y minus p star. P plus y minus p star, right? Just write it like that. And I write it out. So the first term will give me p times hn square of n p. Right, this one we know how to bound it. And we have the remaining 3 terms. But each of them will come with the vector y minus p, which is quite small. Let me write down something. And another term, and another term. So each of these terms will come in with a small norm vector y minus p, which is bounded by epsilon. So this means that this guy is always bounded by 3 times the epsilon times the operator norm of hn divided by square of n. Right. I have 3 terms, each of them coming with a small norm vector. I can use the operator definition of operator norm to get this. Okay. And then I can take the soup among all the y's, right? And then here I will get the soup. I will get the operator norm of this. And I can choose my epsilon to be small, and I can move it to the left side. I hope I have enough time. Okay, so I will get 1 minus 3 epsilon times the operator norm of this guy, right? It's bounded by that one, sorry. So this is bounded by that one, yes. phn divided by square of n p. So here I can choose epsilon to be, say, 1 over 6. Right, if I choose that, and I will get, let's say, this one. the operator norm of the normalized vector actually is bounded by 2 times this guy. Right. If I assume that maybe I erase this one. Then I will get the probability such that the supernorm, sorry, what's that? Hn divided by square root of n. This guy bounded by t. This means that if this is bounded by t, oh, sorry. If this one is bigger than t, this means that this one is bigger than t, right? So this means that this guy is bigger than t over 2. So this means that this should be the probability such that all the lattice point, pi epsilon. This is the p star Hn divided by square root of n p. This is bigger than t over 2, right? And here I can split the maximum by, take the sum. The probability such that the p Hn divided by square root of n p is bigger than 2 over t, right? And for this guy, we can use this argument here. Each of them, I will get some constant c e to the minus c n t square, something like that. And here we know the size of the lattice, size of the the size of epsilon net is say 3 over epsilon to the power of n, right? And if your t is sufficiently large, this one dominates that one, right? So you will get some exponential decay things, something like that. Okay, sorry. Next one. So this means that if you choose your t sufficiently large, the probability such that the operator norm is bounded by is bigger than this constant is exponential small. Then you can use Borel-Kant lemma, right? Sum over that, and this is summable. Then you show that actually your Hn divided by square root of n, the operator norm, is bounded by some constant, almost surely. So that's the proof. I want to mention that here, the proof is so simple because we rely on this concentration inequality for sub-Gaussian random variables. If you have some heavy tilt, the result is also true, but the proof will be much more complicated, so I will not present it. Actually, the optimal should be that as long as the force moment is finite, you should always assume that, you should always see that the largest operator norm is bounded by some constant, almost surely. Yeah, but the proof will be much more complicated. Okay, so any question? Yes. A force moment assumption. Yeah, you have to assume that force moment is finite. Maybe something slightly force moment, I think. So as long as the force moment is finite, you should observe that it's almost surely bounded. Yeah. Okay, so that's a proof for the largest eigenvalue. Almost surely means that that's almost surely. Yes, because it's not on the same space, right? You're saying that. Yeah. But, here, yeah, I cheat a little bit. You can always assume that you have a larger space to include all these random matrix entries. Yeah, Yeah, anyway, I cheat a little bit here, sorry. That's true. The definition, that's the definition of the Wigner matrix is a bit cheating. Anyway, so that's the proof for the largest eigenvalue. Because here we know that almost surely the largest eigenvalue is bounded by some constant, right? So this means that this means what? This means that this is really the correct normalization. And then the next question would be the question 2. Now we know that Hn normalized by square of n is correct order. And we want to know how the eigenvalues of this. So what is the distribution? What is the eigenvalue distribution? Of this normalized matrix. To study the eigenvalue distribution of the normalized matrix, we introduce the so-called empirical spectral measure, which is, you can also view it like the counting statistics of the eigenvalues. The counting measure, sorry. Counting measure. So it's defined to be just the define. This is called the empirical spectral measure. It's defined to be 1 over n summation. Summation. Delta lambda I dx. Okay. So this is a property measure, right? Because the total mass is 1. And you assign, so for each eigenvalue of the matrix, you assign the weight 1 over n, they are equivalent. So actually, if you for any interval on the real line, and you can compute this the measure, which is exactly given by the number of eigenvalues inside this interval divided by the total number of points. So this is exactly the counting measure of this process. Okay. Counting measure. And then, because it's a random measure, so first I have to make sense of the convergence of the random measure, right? So to define the convergence of random measure, and the random measure. Okay. So the idea is to define it in a weak sense. So we just pick any test function belong to a sufficient good space, the continuous function that are bounded. Okay. For any test function inside this space, I can always take the integral with respect to this measure, right? So this is exactly the 1 over n summing over all the eigenvalues against this test function. Okay, and now I get a standard random variable. Then you can use the convergence of random variable to define the convergence of the random measure in a weak sense. Okay, so if I see mu n converge to something, this means that for any test function, I take the integral, and this random variable will converge to the integral of this guy. So that's the definition. Okay. And here is the factor 2. It's a celebrated semicircular, or maybe many of you have already heard this. So it's proved by Wigner in 1950s, I think. It shows that actually the random measure will converge weakly to a deterministic measure almost surely. And the semicircle distribution is defined to be 1 over square root, sorry, 1 over 2 pi 4 minus x squared dx. Sorry, indicator x belongs to -2 to 2 dx. So the distribution looks like that. -2 to 2. They have the semicircle distribution. And here, actually, you can see that if I say this converge to this, it means that this converge to a deterministic number, which is given by the integral of this test function with respect to the semicircle distribution. So actually, the semicircle law can be viewed as a law of large numbers, right? Because they are random variables. You take the average of them, it goes to a deterministic number, which is determined by this limiting measure. So it's exactly a law of large number. Okay. And actually, there are many ways to prove the semicircle law. And one of the most classic way is to use the moment method, because here we have already shown that almost surely the largest eigenvalue is bounded by some constant, right? And we know that if you have a test function, then you can just assume that the test function is supported on a compact support, right? And if for test function with compact support, you can always approximate test function by using polynomials, right? And if you have polynomials, things become much more easy, because then you relate the eigenvalues to the matrix entries in a very natural way. Maybe one of the methods is called the moment method. And this means that you choose the function that are polynomials. Okay, and then the linear eigenvalue statistics, then this one will exactly become to the average of the eigenvalues is a part of case, right? And you can further retain it in terms of the matrix entries, right? And then you can write it as the matrix entries, the summing over I, ik, I1, and the hi1, I2, hi2, I3, until hik, I1, right? And then you can, and if, on the right side, you know the moments of if you know the moments of the matrix entries, by some combinatorial, you can also define the moments of the empirical spectral measure. If you know the moments of the spectral measure, and then you know the distribution itself. And the short, I will not present the proof, but I will just give you that. Just say this is the moment of this is the case moment of the empirical spectral measure, and the result is if you let n goes infinity, if k is 2L, if k is 2L, then this will be given by the constant number. Okay, and I will not show you the proof, but if you are interested, you can just use GPT or just check your random matrix book. You can show that. And for the moments, for the case moments of the empirical spectral measure, it will converge to the constant number for the even case, and for the odd case it will get 0. And this is exactly the case moment of the semicircle law. And this will give you semicircle law directly. So that's the general idea to use in the moment method. But in today's talk, I will present a sort of different way, and I will use the so-called the Stieltjes transform. Transform. So what is the Stieltjes transform? So it's more like the Fourier transform. So it uniquely characterizes the probability measure. Okay, and I will give you a definition. So for any the probability measure for any probability measure mu, Okay. And then you can define a Stichient transform. I use mu to denote it. It's defined to be the integral of the 1 over x minus z. X. And it's defined when z is away from the real axis. So this is a well-defined function, as long as the z is away from the real axis. Okay. And in particular, if mu equals the empirical spectral measure that are defined here, okay, then the corresponding Stichient transform will become 1 over n sum over this one, right? By the definition, this is exactly the normalized trace of the resolvent of the matrix. Right. And I will use GZ to denote the resolvent of matrix. Okay. Sorry. Maybe the trace GZ. And if mu equals is given by the semicircular distribution, then you can direct compute it. Actually, this is the mu SC. This is a solution. Explicit solution given by minus z plus square root z squared divided by 4 divided by 2. And this square root is taken with the negative real, so you have the branch cut in the negative real part. Okay, this is the definition. And actually, you can see that this the Stichient transform of the semicircular satisfies a very nice formula. It's just the solution of this, just a solution. Oh, sorry. So the Stichient transform of the semicircular is just a solution of this self-consistent equation. You can solve for that. It's a quadratic equation. This is quite important that we will use this property quite often later, okay? And the Stichient transform is quite useful when you want to prove the convergence of the empirical convergence of the probability measure. So this is a property. So if you see this probability measure converge to mu, this is equivalent to see that the Stichient transform of this measure will go to the Stichient transform of this limiting measure for each fixed z. So this is a property. Actually, from here to here is very easy to see, right? Because you just choose a test function which is bounded. So from here to here is very easy to see. And from this side is not that hard to see because you just look at the imaginary part of your Stichient transform. And you will get, if you assume that z equals, if you assume that the real part of z is denoted by e, and the imaginary part of z is denoted by eta, this will give you the d mu in x. And here you will get, what's that? X minus e squared plus eta squared times eta. This is just the imaginary part of this guy. Just plug in the imaginary part of x minus e plus minus I eta. Right? This will give you x minus e squared plus eta squared and eta. Just a direct computation. And here you see that this one is indeed the Poisson kernel convolution with the empirical spectral measure, right? And this is P eta is exactly given by this. This is exactly 1 over eta x divided by eta squared plus 1. So this is the integral of this is 1. And when eta becomes smaller and smaller, it will become more closer to the delta function. So when eta goes to 0, this Poisson kernel will be approximate like the delta function. Right? Okay. So you simply let, you just, because here you just assume that for each fixed z, this is close to this for each fixed z, right? And you can first let n go to infinity, and then you let the imaginary part of z go to 0. If you let the imaginary part of z go to 0, this p eta is very close to the delta function, right? And the delta function convolution is mu n is very close to mu n, right? So this will approach to mu n if you let eta go to 0. Is that clear? Yeah. So the idea is like, for each fixed z, you just fix z, you let n go to infinity, and then you let eta go to 0. You will get the empirical spectral measure directly. So actually, this is indeed the inverse digital transform. If I give you a digital transform, you just take, if this is digital transform of the certain measure, you just take the imaginary part of this one, and you let the imaginary part of z goes to 0, and you will get the corresponding mu. So this is indeed the inverse Stiegler's transform. I hope it's clear to you. Okay. So now the task is quite clean. So if you want to know that the mu n converges to mu, then it is sufficient to show that the Stiegler transform will converge to this Stiegler transform, right? And we all know that for the limiting distribution, the semicircular, the Stiegler transform satisfies this equation. So this means that I should get something like that. The idea is to get something like 1 plus z mn plus mn squared. It's almost 0, but with some error, right? Because if this is exactly 0, you will get semicircular distribution. The Stiegler transform is semicircular distribution. So, and if you want to know that, if you want to show that mn, if you show that if you plug m in, and if you can show that this quantity is approximate 0, this implies that my mn should be close to the solution of this. How should I see that? Maybe I should define this. I should define a polynomial in z and m. It's given by that, right? So if you know, and we can take the partial derivative with respect to m, I will get z plus 2m. If this guy is non-zero, then I can always solve for m, right? This is the implicit function theory, okay? And this is always good because I assume that my z is fixed. So imaginary part is away from 0, right? So this m, the imaginary part, see, so the imaginary part of this guy is eta. Sorry, I'm just saying that the imaginary part of m is always positive, right? And the imaginary part of z is always positive. It's always away from 0, right? So this means that this is always bigger than some constant. If this is bigger than some constant, this means that you can solve this equation in a stable way, right? So which means that if this polynomial is bounded by some error epsilon, this implies that the solution of this equation should be close to the Stiegler transform. And the error is also bounded by epsilon. This is simply because this So this controls the stability of the solution of the polynomial. Is that clear? I hope it's clear. Okay. And because you are away from the real axis, so this is always bounded from below. If it's bounded from below, this means that the Jacobian is non-degenerate. You can always solve it stably. Okay. So that's basically the idea. So if we want to show that the mu n converge to mu SC, to show this, it would be sufficient to show that the 1 plus the mn plus mn square is almost 0. This idea. Okay. Then how should we do that? So first, I would like to use some concentration inequality. To show that, because they are all random, right? This is not good for us. So I first want to use concentration inequality to show that actually the Mn is concentrated around its expectation with error 1 over n with very high probability. Okay, this is the first goal. And second goal is that we want to show that the 1 plus expectation of Mn times z, expectation of Mn square. I just want to show that this deterministic quantity will approximately satisfy the same equation as the semicircle distribution. Okay. If I have that and I have that, then I can show that. So this will indicate that expectation of Mn minus MSC is bounded by 1 over n with very high probability. Combine these two, I will get the Mn minus minus MSC by their triangle inequality. Mn minus expectation of Mn plus the expectation of Mn minus MSC. This is bounded by 1 over n. Is that clear? Okay. Okay, so to show the first one, the proof of the first one, I'd like to recall a very famous inequality called the Mach diamond inequality. It says that if you have a sequence of random variables that are independent, they could live on different spaces. Okay. And if you know that you have a function in these random variables, if you replace the xk, the k's coordinate, by the independent one that is different from xk. Okay, and you take the soup among all the x1, xk, and this xk prime. And you say this is bounded by ck, by some ck. And then if, then the probability is such that, so this function is concentrated around its expectation. So that's the inequality. So if I know that if you replace the case column by a different one, you take the soup, it's bounded by some ck, then you will get this inequality. Okay, then we can show, we can see how to adapt this theorem into study the MN. So what is my x1 to xn? So my hn, these are random variables, right? And I just pick, my x1 is just the first column, and the x2 is the second column above the triangle, inside the triangle, and the third column, blah, 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 blah. So this is my first column, second column, and third column. It's very clear that Mn is a function in these columns, right? And this column are independent. So you can use this, right? And then you see that if I remove one column, I automatically remove one row, right? So this means I change this matrix by at most, rank 2. It's at most a rank 2 perturbation, right? Actually, the conclusion is that if you, so how to say that? Maybe I just write it like this: xk, xn. So if I replace this xk by xk prime, this means that I replace one row by another one, and I will denote the corresponding matrix. I write it this way: x1, x2, xk, xn. So if I change this to xk prime, then this corresponding matrix I will denote it by hn of k, and the corresponding station transform I also use this one, xk prime xn. So the observation is that if you change the column, if you change the matrix by some, if you give some finite rank perturbation of the matrix, then the station transform does not change so much by using some resolvent identity. So the claim is that, so the Mn minus the Mn, you replace the k column, the difference is bounded by some constant divided by n eta, and just by some n, if IMZ is bigger than 0. So how to show that is quite easy, because hk minus hk, hn minus hk, and the rank of the difference between these two matrices is at most 2, right? So by the resolvent identity, you can show that the Mn, so the Gn minus Gnk, without that value, this should be equal to Gn times the h minus hk times the Gnk. This is a resolvent identity. And this is a rank 2 perturbation, right? So it can be written as some vectors like this. So at most a rank 2 perturbation. And if you take trace of them, and this guy, then you have to use that the operator norm of this one is always bounded by 1 over imaginary part of z. It's quite easy to see, because this is simply the eigenvalues of G is simply the lambda I minus Z. And lambda, they are real valued, right? So the imaginary part of this one is indeed IMZ. So the operator norm of this guy should be always be bounded by the inverse of the IMZ. And the IMZ is away from 0. So this is always a bounded constant. And so the operator norm is bounded. This means that entry bias is also bounded, right? Okay. So this guy is always bounded by a constant order. And you take the average of the trace. This is always bounded by 1 over n. Is that clear? Okay. So this means that this guy is 1 over n. Sorry. Right, this guy is 1 over n. So the square norm of it is exactly 1 over n, right? So this will give you, sorry. I should not put n here, sorry, apologize. Let me check, I should not have n square. Yes, otherwise it's too good. Let me check my inequality. Yes, there's no n here at this moment, okay, for this one. So if my ck is bounded by 1 over n, I just plug in, so this will give you 1 over n, so this will become e to the negative c n t square, and from c, in this case. So this implies that the probability such that Mn minus expectation of Mn is bounded is bigger than t. This is the exponential small guy. And then you can use whatever. You can use the Borel-Cantor lemma to show that actually Mn is really, it's really converged. It's really around sorry. Let me write it. So this means that Mn minus expectation of Mn is always bounded by, maybe I just put some log here or something to make it better. It's always bounded by log n to some power divided by n. With very high probability, right? Because it's just a plug in. And if you, yes. So you see, this is bigger than that. Okay, only show square of n. Okay, anyway, square of n. Did I make any mistake here? Okay, anyway. Yeah, I just say the probability is super exponential small. Something like that. Some exponential. Into some log n to some power. It's just some very large, very small exponential event. Okay. Oh, this is too bad. I thought I could get some 1 over n. I can only get square root of n. Maybe here I lose too much because I use something that is very weak. I just use this concentration inequality. Maybe this concentration inequality is not the best one to use. Now, I wish I could get some inequality like 1 over n, but unfortunately it's only 1 over square root of n. Anyway, let's take it. Now, this here we have shown that Mn is concentrated around the expectation of Mn with very high probability. And this is the first step. And for the second step, we have to show that expectation of Mn is really close to the MSE. So the proof of the second step is that we have to show that the expectation of this one is very close to this. Okay. This is equivalent to show that Mn square plus Zmn plus 1. Okay. Then what should we do? So the idea is to use some very simple integration by parts. So remember that my Mn is simply the normalized trace of my resolvent. And my resolvent is defined to be this. So by the definition of a resolvent, I would have 1 plus Zg equals, Zg, H minus Z multiplied by G is identity, right? So this gives us that Zg is indeed Hg minus 1, just by the definition of the resolvent. Okay, now I just plug in here. Maybe before I plug in, I just take the average trace. If I take the average trace of G, I will get Mn, right? I get average trace of this, I just write it. Just a summation, I just write it out. I will get Hij, G, Gi, and minus 1, right? Okay, and then we plug in. Here, I will get Z times that. And this one will be killed by this one. So I will get expectation of Mn square plus summing over I and J, expectation of Hij times the Ggi. Right. Okay. And you can see that H is a random variable, and J, and they are independent random variable, and J, of course, is a function in this H entries, right? So, for example, if you will just assume that H is Gaussian, then you can use the Stan formula for Gaussian, right? So in the Gaussian case, we always have the Stan formula. So if H is Gaussian, maybe with some variance, and then the expectation of H multiplied by HF by some integration by parts, you can easily get the variance of H multiplied by the expectation of the derivative of this function. This is for Gaussian, okay? And actually, for non-Gaussian, that's also the formula. This could generalize the Stan formula, or you call the cumulative expansion formula. It says that for non-Gaussian H, it can always expand in terms of the cumulants of H. Okay, so I start from, so my K is from 1 to some super large order. And here I will have K minus 1 factorial times the case cumulant. The case cumulant of the random variable H multiplied by the F, the expectation of the K minus 1's derivative of this function, plus some truncating error. And here maybe I stop at L, and here should be L plus 1. It's a truncating chain error. And you can see that the Stan formula is actually a special case of this cumulative expansion, because we all know that for Gaussian, the higher cumulants all vanish, right? So you don't have this high order terms. You only got the first derivative, and it will stop because all the higher order cumulants just vanish. Maybe I should give you the definition of the cumulants. So it's behave like moments. You know that for any random variable, you will have moments, right? And if you know the moments, you can know the cumulants. And they have the relation. And plays the same role as cumulant, I have to say. And the cumulants is very special because for Gaussian, the higher cumulants are all vanishing. It's 0. So actually, it's a very good way to prove the central limit theorem is to use the cumulants. You just prove that the cumulants of something, the higher cumulants of something approaching to 0 is okay. This is much easier than to show in the moments. Right? If you want to show something that converge to Gaussian, you have to show the case moment, converge to the case moment, right? Somehow this is not that easy. But if you to show that the false cumulant goes to 0, it's much more easy. You just bound it by the upper bound is enough. So cumulants is more useful, I would say. So let me, so should I have enough time? So what is my cumulant definition? I just copy it. So the definition of the cumulants is simply the derivative of this case derivative. The case cumulant of the random variable h is simply the derivative of this log of the moment generating function and take a value as 0. So this is the definition of cumulants. And here I didn't write down the, maybe I erase this one. Here I didn't write down the bound for the I didn't write down the bound for the truncating error. Actually, I just copy it quickly. Usually the truncating error is not very important, so it is bounded by this. So part of L plus 1 and the sub among all x bigger than. Where M is arbitrary cutoff. So in our setting, it's better to cut off H. It's better to cut off H at the level into the -1/2 plus some small epsilon because we normalize by our entry by 1/√n. So it's better to cut off slightly beyond this typical spacing, typical size. Okay. In our set, we just choose this one. Okay. And you can see that because our H is normalized by √1/√n, right? So higher cumulants will become smaller because the cumulant, the case cumulant of A times H is equal to the A to the power of a case times the cumulant of H. If I normalize my H, my square by √1/√n, I get more from the higher cumulants, right? My higher cumulants will become more and more smaller. So that's the reason. So these higher order cumulants, they are smaller than the second order cumulants. Okay, so that's the reason why you always observe the universality, because only the second cumulants contribute. The higher order moments does not contribute that much. Okay. And then move on to our proof. So we have there, right? So what is the summation? Hij. Oops, sorry. And HGI. Oh, actually, I forgot to say that if you want to see the proof, actually it's better to start with a polynomial f test function. If you choose f to be polynomial, this is just the moments, right? And this will exactly become the relation between moments and the cumulants. You know that there's a relation between moments and cumulants. On the right side, you have the moment. On the right side, you have the cumulants. And if you have general test function, you just do some Taylor expansion. You will prove it. It's not that hard. Okay. Now we use it to compute this guy. And for simplicity, I just keep the second order cumulants because higher cumulants they are even smaller. You can trust me. Okay, I just keep the second order cumulants. Sorry, I forgot 1/n here. Now you should have stopped me when you spot some mistake. Sorry, it's 1/n. Okay. And the first order term is given by 1/, because the variance is 1/n, right? I get an additional 1/n. This is summation I and j. The expectation of partial gi, partial hij. Right? This is the first order cumulants. You can just look at this stand formula here. This is the first order right? And multiply by the variance. And the variance is 1 over n because we normalize the matrix by 1 over square root of n. Okay? And here we need to take a partial derivative of the matrix entries. And it's not very hard to see that, you know, this is simply the G, you know, if your HIG is on the upper part, if you change this, you will also change this guy, right? So you have two terms. So the first term is coming from IJ entry, a minus here. And the second term is from the GI's entry. I only talked about the real case, and the complex case is something similar. Okay, so you got two terms. So it's G delta GIG. So if you change HIJ, you will get IG entry. You will also get the GI entry. So you get two terms. And if you are on the diagonal, you will only get one term. Say partial G, partial HII. You will only get one term because there's only one term here. Okay. Now I should write it a little bit different because we know that maybe I cheat a little bit because, you know, I cheat a little bit because, so we only have the random variables when I is less than J, right? So, I mean, maybe I write it like this. IJ2 summing over I less than J and plus 1 over n summing over I expectation of HII, GII. So they are corresponding to the upper diagonal part. This is corresponding diagonal part. Yes, please. This means that there is one at the IG's column and others are just 0. And this is the same here. Oh, yeah. Okay. And you just do them, you know, just do it separately. And if you believe me, because I don't have much time, so maybe I just write down the result. So this is, well, sorry. Maybe I should just the 1 over n summing over diagonal part, expectation HII, GII. Just do them separately. Okay, IJ, and here I get GGI, HIJ, and here I get 1 over n squared, and the partial GII, partial GII. Okay, and here I will get two terms. Sorry, I less than J, I less than J. I will get two terms. The first term should be GIJ, GGI. And the second term should be a negative sign in front, a negative sign here, okay? So I get GII, JJJ, right? Because if I put IG here, I will get IJ, IJ, right? This term will give you IIJJ, right? This term will give you IJGI, okay? And same here. I will get one term, so it's GII, GII. That clear? Okay, so I can further write it as a matrix product, right? Because here I only have I less than J, and I include this I equal to J, I will get 1 over n squared summing over I, all the indices, GII, GJJ. Right, plus GIJ, GJI. Maybe I lose some off-diagonal term, but off-diagonal term is not very important because this is bounded by 1. Right, this guy itself is this order, this is bounded by 1 over n already. Right, because G is bounded by 1. You take the sum and it average normalize by 1 over square root of n. So this is not very important. Okay, and I forgot the expectation. And you can see that this is indeed the mn square, right? This is indeed mn square. Sorry, I forgot the minus sign. Sorry. This is indeed the mn square. So it will cancel with this guy. Is that correct? So this guy, you will get some minus expectation of mn square, because this is GII, JJJ, and summing over I and j. This is the mn is the summing over this one, right? And if you square it, you will get 1 over n square ij GII GJJ. This is exactly this guy. And you got additional term, which is given by the 1 over n square trace g square, right? Because here is GIJ JJI. You're summing over IJ. And of course, you have some error term like this, okay? And this one will cancel with this guy. And how to control this guy, this is also very easy. We just use the Cauchy-Schwarz, right? This is bounded by 1 over n square trace G star, right? And this is bounded by G minus G star. And you know that G star it can be written as G minus G star divided by Z minus Z bar, right? And here you will get G minus G divided by the imaginary part of Z, 2I, right? And this is away from 0, right? So you know this is indeed bounded by 1 over n, because this is bounded by 1, this is bounded by 1, right? Okay, so this means that you can prove this guy, you know, by this computation, you can show that it's indeed bounded by 1 over n. So that's the general idea of to prove it. So let's make a conclusion. So the first, we use some concentration inequality to show that, here, we use some concentration inequality to show that the M is concentrated around the expectation of M with the error one of square of n with very high probability. And then we compute the expectation of Mn by using the Kuhn expansion formula. And we show that it's indeed very close to MSC with error 1 over n. That's the idea of the proof. Any questions so far? Okay, so these are about the how to show the law of how to show the semicircle distribution. This proves the semicircle distribution, which means that you show that mu n converges to mu sc as n goes to infinity almost surely. Okay. And in the next lecture, I will show you how to prove the semicircle law on the local scale. And here we see it's global scale. Why? Because we first let n goes to infinity, we fix z, and let n goes to infinity. We show the error is small. And the local scale means that you let your imaginary part of z also depend on eta, also depend on n. You do not first fix z and prove the convergence. You let your z also depend on eta, also depend on the n. Why this helps? Why this helps on local scale? Why this is so important? Because you can see what is my imaginary part of mz. This is more or less this guy. This is exactly this one. Eta lambda I minus e square plus eta square, and my z is e plus I eta, right? If you let your eta depend on n, see 1 over n to the power of alpha. So this stuff is more or less, it's forming, the main contribution of this guy is more or less the number of particles in e minus eta, e plus eta, divided by 1 over eta, right? Is that clear? Because when lambda I is close to e on the scale of eta, it contributes something. Otherwise, it's very small. Because if this is much bigger than eta, you know, it's much small. This is more like deterministic guy. So the only contribution is coming from the lambdas that are super close to eta on the scale of eta. But you cannot let eta to be too small, right? Because if you let too small, you don't have any law of large numbers. So you have to let your eta to be not that small to control, so you want the number of particles inside this interval still infinite many as n goes to infinity. Then you can observe some law of large numbers, right? So the local law means that your eta should be much bigger than the typical eigenvalue spacing. As long as your eta is much bigger than your typical eigenvalue spacing, there should be infinite many particles inside this interval. So you should still observe some cancellation among them, right? And you should see that actually this should convert to some deterministic number as well, even though your eta now is decaying with respect to n. So the local law means that Mn is still converged to MSC. You do not fix z, but you let your imaginary part of z to decay in respect to n. And this alpha cannot be too large. It has to be bigger than 1 over n, which is the typical spacing inside the bulk, because you have this many eigenvalues, right? It's supported, all the eigenvalues are confined in the interval from -2 to 2, and you have n eigenvalues. So typically speaking, the eigenvalue spacing here should be 1 over n, right? So the local law means that if you let your eta to be much bigger than 1 over n, the semicircle law is still true. So that's the local law. And I will show you how to prove the local law next time. Okay, thank you.